So let's start off by looking at impurities in water. Can you guys see this okay?
Yeah.
Yeah, it's okay.
Thank you. Okay, impurities in water. And so let's start listing the kinds of things that we find in water. Things that we've got to remove.
Biological impurities.
Okay, biological impurities. Boy, sure. Let's put these over here. Biological. There we go. All right. What else?
Can we say TDS?
Dissolved solids. Okay. So I think I'm going to put those over here. Okay, what else?
Non-contact gases.
Sand. Okay, so let's just call that suspended matter. And so sand is one of the things that we put in that category, or silt, which is really like fine clay, stuff like that. Okay, give me some more.
Dissolved gases.
Dissolved gases. Okay. Give me a couple of those.
Carbon dioxide and oxygen.
Those are a couple of our biggies there. Those are our main concerns. There can be other ones too. There can be H2S and stuff like that. Anything else? Let's go back to the dissolved solids here. What kind of dissolved solids are we talking about?
Calcium,
Simply calcium and magnesium salts. Okay, so in particular, calcium, I mean, there are lots of things that can be dissolved that are not calcium and magnesium salts. So specifically, when we got calcium, magnesium salts, that's hardness, right? Okay, somebody was just saying something else. I talked over them.
Sodium?
Say that again?
Sodium?
Sodium. Yes, certainly. Sodium. So yes, again, sodium salts that are dissolved in the water. How about silica? Silica is SiO2. And we can also have iron salts, dissolved iron in the ground. So where am I going with this? What we have are impurities that really depend in part upon the source. So if I've got groundwater, and groundwater is basically comes from a well or from an underground spring, we're going to be more likely to find various dissolved solids because the water has resided within a geological formation that has things like limestone, and limestone is where we get the calcium and magnesium from. Or water has been in an underground formation that has a lot of sand in it. And so that's where we get the silicon dioxide, because that's what sand is. It's SiO2. Sodium could be infiltration of brackish water, but you know, there are underground salt formations. And depending upon the soil, the water could be in contact with iron. And of course, we know that and we can also get iron compounds and find these dissolved in the water. So these are all examples of impurities that we primarily find in groundwater. Whereas the ones on the right-hand side here, these are impurities that we find more in surface water. And by surface water, we mean rivers, lakes, that sort of thing. Okay, so let's say, for example, we've got a waterfall. We might find the aeration effect of a waterfall is going to add oxygen and CO2. And not only that, just simply having the body of water exposed to the atmosphere is going to be more likely to dissolve O2 in it. And as for suspended matter, the sand and the silt, this is the type of stuff that gets filtered out through the groundwater. So for example, if I've got a well, or if I've got some kind of a spring, that's water that's coming from the ground, from an underground aquifer, and the aquifer itself has a filtrating effect. So basically filters the water and removes a lot of the kind of suspended matter that we see in surface water that we don't get with groundwater. And as for biological impurities, I guess we could lump together things like leaves, algae, anything that may require disinfection, for example. So these are the types of things that we find in surface water. And so ultimately, when we are looking at the kind of external water treatment in preparing this for boiler water, we have to consider the source. Now, in the plant where I worked at the generating station, we had both sources. One source of water was river water, and the other source of water was a ground, like a deep well source. And so the deep well water had a fair amount of iron in it. The deep well water had some silica in it, and their deep well water was fairly hard. Now, as for when we switched over to river water, we had screens to remove the biological matter, but we had to deal more with the suspended matter, sand, silt, that sort of thing, because this water was relatively soft. And we see that with surface water. Compare that to groundwater, this stuff was relatively soft. So when we switched over, we had to change how we treated the water from an external basis. So how are we going to treat it? Let's say, first of all, we've got water that's from the ground. The groundwater, we know, is going to have the silica. Okay, what's going on here? There we go. The groundwater is going to have silica. It's going to have hardness in it. So what we need to do is basically our first steps, because we don't have a lot of suspended matter, what we're going to do is aerate. And aeration, basically what I'm going to do is I'm going to take the water and I'm going to cascade it, and sort of the exact opposite of a deaerator. Now there's this Dalton's law of partial pressures, and you know about that from deaeration, mechanical deaeration. So the concentration, the the concentration of a particular gas in solution depends upon the partial pressure exerted on the surface of that water. That's Dalton's law of partial pressures. And so then you think about, well, aeration. Basically what we're doing is we're exposing so much water to the air, and we're actually going to maximize the concentration of oxygen in the water. And you think, well, that's not good because we want to deaerate the water. But aeration does a couple of things for us. First of all, if there is dissolved CO2 will be liberated through the aeration process. So that's the first thing that it does for us. But more importantly, if we've got iron, what we're going to do is take ferrous, FeHCO3. Okay, so ferrous bicarbonate. This is a soluble form . It's soluble, right? And so here's what happens with this iron bicarbonate. If that gets through to any ion exchange resins, so if we've got sodium zeolite softeners, if we've got demineralizers, if we've got dealkalizers, anything that has an ion exchange resin, the iron will foul the beads, or just say wreck the beads. So it wrecks ion exchange resin. So we don't want that. Resin. So what we're going to do is, through aeration, we are going to take FeHCO3 twice and plus oxygen, and it's going to give us some insoluble iron oxide plus CO2. And the reaction escapes me right now. Let me just check and see if I got it written down. I don't, but I'm just going to write down insoluble iron plus CO2. So that what that means is that the iron is going to precipitate, it's going to come out of solution, and then what we're going to do is the next step, after we aerate, we're going to filter the water with an iron filter. Now, I don't know what the groundwater is like here in Alberta, because I haven't worked in well, yeah, I guess I worked in northern Alberta where we had very high silica, but I don't think that we had much in terms of iron. Anyone here from, say, like an Alberta farm where you can comment on the well water, and do you have a lot of iron in the water here? Well, back in Manitoba, where I'm from, outside of Winnipeg, if you had well water, you had a lot of iron in it. And it was also hard water, so what we wanted to do was run it through a sodium zeolite softener. But before you ran it through a sodium zeolite softener, we had these things called Patterson iron filters. And a Patterson iron filter was brilliant. What it had was a little aerator, so the well water would go through an aerator. The aerator would put a bunch of atmospheric air into the water, forming this insoluble iron form, and then there's a filter downstream of it that would filter out the iron, and that way you wouldn't wreck your softener beads. So anyway, we're going to now do this, but on an industrial scale. So if we've got water that doesn't have a lot of suspended matter, we're going to basically aerate it and filter it to get rid of dissolved iron, and also to get rid of dissolved CO2 if we happen to have some in there. But let's say we've got a lot of suspended matter. And so suspended matter, we're going to have a different step one. Okay, what we're going to do is, first of all, slow the flow. And so what we're going to have is something called the clarifier. So in the clarifier, the heavier suspended particles, well, one of the reasons that the suspended matter is suspended is due to the velocity of the water. So if we slow down the water, these suspended matter comes out of solution, or actually not out of solution. It's not dissolved, but it comes out of suspension. Heavier particles will come out of suspension as the water slows in velocity. So this is what I'm trying to say. Reduces velocity of water. And so heavier particles drop out. But what we likely have is something called turbidity. You folks know what turbidity is? It could be color in the water, maybe taste, maybe cloudiness. Anything that gives the water sort of a cloudy appearance or a color hue to it. And the thing about turbidity is it's made of suspended matter that will deposit and plug up in our boiler. But it's not stuff that falls out on its own. So what we need to do is do two steps. First of all, coagulation. And then the next step is going to be called flocculation. And then after that, basically it's sedimentation all over again, where we just allow it enough time for it to settle out. Okay, so we start off with two different types of water sources, and they got two different characteristics. The one on the left is groundwater. It's going to have silica, it's going to have hardness in it. But step one in that water doesn't involve removing any of the hardness, doesn't involve removing any of the silica. What we're going to do is aerate it and filtrate it if there is dissolved iron in the water that can foul the resin beads. On the right-hand side, you see the surface water stuff, and so biological matter, suspended matter. We're not going to do anything in step one about the dissolved gases. But what we are going to do is deal with biological and suspended matter, and through the clarifier. The clarifier is going to slow down the water flow. There's going to be sedimentation, and in order to assist the sedimentation, we'll add some chemicals called coagulants and flocculants, and what they're going to do is remove the extremely small particles that we call colloids. So here is what the clarifier does. So in this slide here, you can see turbidity, right? I mean, so it's adding cloudiness and color, and this one here obviously has the most turbidity, and this one here has very, very little turbidity. And we can actually measure turbidity with a turbidimeter, believe it or not, and the turbidimeter is going to give us turbidity in NTU. And NTU, people might wonder, well, what the heck does that mean? It's nephelometric turbidity units. You can look that up. I'm not making this up. You can't make it up. Nephelometric turbidity units. So that's why we just say NTU. So not only So you think, okay, well, look, this stuff here is so fine. It's so, this colloidal material, the colloidal material that we see dispersed in here that adds the color in the cloud, you think there's very, very little matter there. How is that going to be a problem? Well, in a boiler, it's going to accumulate because, of course, we're driving off pure water, and there goes our pure water, and we're putting in impure water, and so we find that the amount of impurities increases in the boiler, and in the case of a suspended solid, it's going to coat the heat transfer surfaces. It's going to impede heat transfer, very much like scale does. It's not the same as scale, but it has a similar effect. So by suspended solids, we have to emphasize this stuff is not dissolved. Okay, this stuff here is suspended. And then you kind of say, well, why doesn't it just fall out? Why doesn't gravity just cause this stuff to fall out? Well, sand and silt and clay can be removed by gravity and sedimentation. Which is something that goes on in a clarifier. But colloidal particles have little charges, and I don't know exactly what the charge is. I'm going to put little plus signs on them. And here's the things, that they all have the same charge. It might be a negative charge. I really don't know, but I'm just making this up right now. They're just charged particles, and they're so small, and because they have these charges, they stay very dispersed, very evenly dispersed throughout the water, and gravity cannot make them come together at the bottom, right? I mean, we would want them all to sort of sink to the bottom and leave us sediment in the bottom, then we can deal with it, we can discharge it. But those little charges, how do you bring them close together when they all have the same charge? So gravity cannot work. And by charge, we're talking about a surface charge. We're not talking about an ionic charge. This is just simply a surface charge. So one of the things we've got to do in the clarifier is to get rid of colloidal material. So here you can see a series of steps, and what has happened here is they put a coagulant in with the water, and they got a little mixing thing here. And this is just for some sort of a test. So then this thing here is going to spin around, and it's a little paddle. It's going to mix the coagulant, and notice what happens is over a short period of time, this is 1, 2, 3, 4, as time progresses, the coagulant has basically stripped away the charge, and now these little charged particles, these colloidal particles, are coming together. And so basically what we've done here is we've added a coagulant. And then what we'll also do is we'll add something called a flocculant. And a flocculant is going to sort of help the particles adhere to each other into a larger clump. So the coagulant is making these little things that we call flocks. So all of the little visible colloidal particles now are called flocks. And a flocculant causes the flocks to come together into larger flocks. So flocculant makes large flocks. And so here you can see, you know, these large flocks. And guess what? Once you have a flock, gravity causes it to settle out, and now we can dispose of it. That's what we want to do. So, so let's just take a look at this particular one. This is called an upflow sludge blanket clarifier. So what we have in there is a sludge blanket. And let's say that the sludge blanket, that looks like it's the top of it. Okay, and so here's what we got going on. Motor on top, little electric motor, a shaft, and we've got all of these stir sticks in here, paddles that serve to mix the raw water with the coagulant. And then on the bottom, we've got a large sort of scraper here. And the whole idea with this bottom scraper is to move the sludge toward the blow-off. So they're calling that the precipitator drain, but I'm going to put a blow-off valve on there. So basically, because that paddle is moving in a circular direction, it pushes the sludge out toward the outside. So you can see here where the sludge is most concentrated. Actually, no, they're showing that that's the drain. They're showing the sludge blow-off line is here. Okay. Main thing is that we're blowing off sludge at the low point of this. And I'm going to spend a little bit more time on the clarifier, because once we get into the precipitation softener, whether it's hot lime or cold lime or warm lime softener, it's basically the same principles, okay? So the raw water comes in, and the raw water has colloidal material and perhaps some other suspended matter. And we are going to inject a chemical in. So that'll be the coagulant and the flocculant. And so it gets mixed here, and this is not a chemical reaction. Okay, the chemicals that we are adding do not react with the dissolved particle, or not dissolved particles. I gotta stop saying that. Suspended particles. There's no reaction going on here. All there is a stripping away of electric charges and sort of a bridging together of the tiny little flocks to form large flocks that fall out of suspension. So the flock that has fallen out of suspension is called sludge, and that's actually a really good thing, because what's going to happen is it's going to filter the water. So water comes in, we add the coagulant, we start to see very tiny flocks forming, and then form larger spongy flocks like we saw in that diagram. And then before you know it, we've got this really dense sludge down here on the bottom. Notice the shape of this vessel. It's cone-shaped. So think about a river. The river comes in to a lake, and so we have a fairly high velocity of the water going in and carrying a lot of suspended matter. And then when that water enters into the lake, the velocity slows tremendously, and it no longer has the energy to carry the larger suspended matter. So whenever we see a converging nozzle or any sort of a convergence of fluid, we see its velocity is going to drop. And in the case of this here with suspended matter, the suspended matter will drop out, the heavier stuff. So notice we've got the converging cone shape, and the reason there's a converging cone is to slow down the water as it travels through the clarifier. Then what's going to happen is the water is going to turn around like that and continue to go through the sludge. And so all of the flock that precipitates is basically going to get filtered out by the sludge. Again, we've got this convergence, and that convergence is going to slow down the water flow even more. And then what we get above the sludge blanket level should be clear water, very low turbidity, and that water will flow over a weir through these little holes here. The water will flow through these little holes and it'll spill out, and then there's our effluent. Okay, so 2 words here that you need to know. Influent. You need to know the word effluent. Influence going in, effluence coming out. So how do I erase all the ink on the slide? I do it that way. So what we're going to try and do when we control this, we're going to, first of all, we want to maintain a constant sludge blanket level. We don't want the sludge blanket to get too high, because then we start to carry over into the effluent, and we don't want that. And we also don't want it too low, because then we may have insufficient flock and sludge to adequately filter out the flock that's forming. So just like in Goldilocks and 3 Bears, we want the water, the sludge blanket level to be just right. So how do we do that? Well, we've got basically it's like tricox. So we've got these 4 lines here, and these 4 lines are going to sample the sludge at various points. Now this very top one, probably will give us clear water. If we start to see sludge coming out of that top sample line, then we know that we're running the bed too high. We'll talk shortly about what we need to do to get the bed where it's supposed to be. Notice that I'm talking about operation stuff that the text is kind of silent on, and I want to prepare you folks for when you work in a plant. I mean, if you work in SAGD, you're going to have warm lime softeners, that type of stuff. And so precipitation softening is a big thing. Even though this isn't a precipitation softener, you're going to see that a lot of the same principles apply. So the top one, we want clear water, but in this one here, we're going to want to see some sludge. But it's going to be fairly thin. And then this one here, we'll see some thicker sludge. And then here we should see, fairly thick sludge. And so what we're going to do is we're going to take, say, 200 millimeter graduated cylinder. We'll take 4 of them. You know what a graduated cylinder is. You've used them in lab, and maybe you've studied chemistry in the past. Okay, so we've got these graduated cylinders, each one corresponding to one of those 4 points on the side. And so let's put these from left to right, the same order that we have these ones, okay? So this one here is going to give us thick sludge, and so we're going to fill it up to the 200 milliliter mark, and maybe we're going to wait 10 minutes, whatever the procedure says, and we're going to find that the sludge level is quite high, and maybe there's a tiny little bit of water on top of it. Then we go to the second one here, maybe we'll see something very similar, but maybe just a little bit more clear water on top. And then we get to this one here where the sludge is quite a bit thinner. After 10 minutes, we might see that the sludge is there. And the one on the right might be clear water, where we might just have just a little bit of sludge in the bottom. Okay, so this is one of the things that you're going to be doing on shift on a regular basis, maybe, I don't know, every 2 hours, maybe 4 hours. You're going to be doing this because what you're trying to do is figure out the bed density and you're also going to try and figure out the bed height. We don't want it too high, we don't want it too low, and we don't want it too thin, too watery, and we don't want the bed too thick. So how do we control this stuff? First of all, our blow off, if we increase blow off, then what are we going to do? We're going to lower the bed, and we are going to make it make the bed thinner, and we're also going to reject chemicals that we might kind of like. You know that this is one of the problems with too much blow off, is you blow off chemicals, and that's a good thing. So too much blow off gives you all that kind of stuff. But let's say that we need to lower the bed level. That would be an appropriate thing to do, would be increase the amount of blow off. And if we wanted to raise the bed level, we might reduce the amount of blow off. So if this bed becomes too thin, and maybe our bed level gets too low, then we would decrease the blow off. So when we decrease the blow off, bed level rises, just simply because we're not discharging as much sludge. And the bed becomes thicker. Okay, so these are some of the things that we can do during operation to look at the bed level and adjust it properly. Now, there's something else that we may want to do. So we find that the rate of influent is also going to adjust the bed density and the bed height. So under really steady state conditions, you know, we've got a certain amount of makeup water coming in from the well or the river or whatever. And if everything is stable and very steady, this thing here is pretty good. But if you're expecting an increase in makeup water, if you're expecting an increase in flow, then in anticipation of this increase in flow, we might want to lower the bed a little bit, because we know that the increased water flow will expand the bed. So if flow drops, influent flow drops, becomes, you know, negative, I guess, negative reduction in influent flow, then the bed drops. If the influent flow goes up, then what we find is that the bed expands. And we don't want the bed to expand so much that we start to see carryover through the weir. We don't want carryover. So the control room operator is going to know that there's going to be an increase in load, and if there's an increase in load, then they may require an increase in influent flow. And so the control room operator might say, hey, you know, we're going to increase the blowdown a little bit and drop the bed a little bit, because our our flow is going to be going up by 20%, something like that. How's the sounding? So, what exactly is keeping these particles here at the surface of the bed? So at this point, they're no longer colloidal. This is flock, and it's flock that has somehow risen to this particular level. And so why do they just stay there? So because they are now heavier particles, because they've coagulated together, there is force of gravity on those particles. But then there's also on those particles, there is a force of the water flowing upward. So there's another force. And where those forces equalize, that's where the bed level is. Ain't that neat? Now, because this all takes time, we have this thing that we call residence time. And so the longer the residence time, the more opportunity for gravity to pull the particles out of suspension. So we're talking about, I don't know, maybe say 2 hours. I'll put a question mark behind there. What that means is that the water comes in and it takes it 2 hours to go through here, to make the flock, to come out here, and to go out into the weir. Okay, so then the last thing I want to talk about with this is the chemical feed. How do we know how much chemical that we got to feed? Well, we're going to put a control valve there on the chemical feed line. Or actually, probably what we're going to have is a pump that starts and stops. And on the influent side, we're going to have a meter. And on the sludge blow-off line, we're also going to have a control valve to give us an automatic blow-off of sludge. So we know what the composition of the water coming in. The water coming in has a particular NTU. And so knowing what that NTU is and knowing what the rate of flow is, they know that they need to add so much chemical, so much coagulant. They need to know so much flocculant. And then they also, based upon the rate of flow and the NTU, we know the rate at which flock is going to form. So that is also going to inform us on blow-off, frequency and duration. Frequency and duration. So you think, oh, this is so complicated, Dave. I'm going to be working in a plant, and oh, I gotta. Well, okay, it's kind of like riding a bicycle or driving a car. You kind of get a feel for it, right? And so when you're a water reuse operator, you get a feel for it, and after a little while, you can just sort of apply your knowledge. But really, what we have is a controller. We've got this brain here. Okay, there's our controller brain. And so based upon the influent flow and the water lab testing, we have an output signal that controls how much chemical is being fed and also controls the rate and duration of blow off. So all we're going to be doing is maybe just fine tuning things, or maybe doing the occasional manual blow and stuff like that. I wanted to show you this aerator here. This is at the generating station where I used to work, and like I said, we had a fair amount of dissolved iron, and that was a real problem. It formed deposits in boilers, yes, but the big thing for us was it fouled the ion exchange resin. So we had a demineralizer bank in our plant, and this would have just wrecked it. And as for the reaction, that reaction forms ferric hydroxide, which is a flock, and it actually precipitates in there, and we're going to use an iron filter. So those are the iron filters at the generating station where I used to work. So 3 banks of iron filters. And so this was taking water that came directly from that aerator, from the Coke tray aerator. But we're still on clarifiers. So what are coagulants? Usually we use inorganic compounds, and they would be iron or aluminum salts. Iron salts are pretty common. They've got a very broad range of suitability. But aluminum salts, I think, might be more common. And so the main ones are aluminum sulfate and alum. And I do believe that aluminum sulfate is alum, but if we're talking about the concentration, aluminum sulfate itself, we're talking about 17% Al2O3. Oh, aluminum oxide. That must be a typo. Or 8.25% is alum. But anyway, this is an important one. You need to know what alum is, or aluminum sulfate, Al2SO4 3 times. You should also know sodium aluminate, and I would say no ferric sulfate too. Anyway, so these are inorganic, and these are things that actually cause the coagulation to begin, and so it gets rid of those colloidal particles. Whereas flocculants are some kind of polymers, and we add them and they bridge the particles together and make large flocks. Yeah, okay, so 1 to 2 hours of residence time. Water flock recirculates. Know these 2 terms here. Solids contact clarifier and sludge blanket clarifier, they are the same thing, but you hear both words back and forth. Okay, solids contact and sludge blanket. Basically what that means is we make the sludge blanket, and the water goes through it. So as the water makes, as a coagulant makes the little pin flocks, get trapped in the other sludge, and so that's why they call it a solids contact or sludge blanket clarifier. Aeration, eh? Well, here's that reaction that eluded me a little bit earlier, but this is iron bicarbonate, ferrous bicarbonate, or iron 2 bicarbonate, if you want to call it that. And then when we aerate it, we add the oxygen, and along with some H2O, we get ferric hydroxide and carbon dioxide. So obviously this stuff here is a gas and leaves the top of the coke tray aerator. And this stuff here is actually, it's a flock. So, and it's a insoluble precipitate. So this stuff here is soluble, and it causes us problems. And this stuff here is insoluble. So that stuff there's a precipitate. Okay, there's the coke tray aerator. Can't really tell you much about that, other than this bottom part is a holding tank. Okay, there's a level transmitter that tells us what the level in the coke aerator is. You can see some piping here. This pipe here is actually going to the top, and it's going to spray into a distributor panel. And then inside here, you can see there are these louvers. Inside here, there's so many chunks of coke. Basically, it's coal. You know what coke is. Filtration, yes. Okay. So then, after we've either clarified or aerated the water, then the next thing is we filter it. So in the case of where we had groundwater that had iron in it, the filtration step is to get rid of any iron flock that may have been carried over. Aeration removes dissolved solid, and then filters. Yeah, so removes iron flock that gets carried over from the coke tray. But if it's surface water, we've gone through a clarifier, and in that surface the surface water clarifier, we might get a little bit of carryover into the effluent. So wherever we've got a water clarifier, or we've got an aerator, or if we've got a lime soda reactor, then what we'll do is we'll filter the water, we'll filter the effluent afterwards to get rid of any sort of carryover. So which brings us now to gravity and filters. Yeah, basically anything's carried over. Now, a common material is anthracite. And so let's consider a situation where we have got, say, precipitation softening, and this is going to be a hot lime soda precipitation softener. And so we have clarified water going in. Clarified and maybe aerated water. Goes into the hot lime soda softener, and this might be, say, 110 degrees Celsius in there. And so we're removing scale forming compound, we're removing dissolved solids, and we're removing silica. The effluent from the hot lime soda softener, we need to filter it. So we got a filter bank here, and if those filters contain silica sand, okay, so sand is Si Well, we've gone to great pains in here with our hot lime soda softener to remove silica. And then we take that hot water, we're going to put it through silica sand filters. So for that reason, we do not use sand filters. Not sand filters. Yeah, we don't use them because we're going to end up redissolving silica. Okay, and silica, if you're aware, last year you probably learned that it deposits on turbine blades. It makes a very hard scale inside of boilers. It's very hard to remove. So we really don't want to use silica sand filters. So there are a couple of types of filters that are referred to in your textbook. First of all is the gravity filter. These are maybe less common. Now, they're open vessels, they're open on top, and so our inlet water comes in and it carries with it various flocks and carried over material. This one here is actually going through a bed of sand. Like I said, it doesn't have to be sand. And then there's also gravel, and then the effluent goes out that way. So that's the normal service. Now at some point, I'm just drawing particles of impurities here. At some point, and gets really packed up with impurities, and we're going to have to get rid of that by doing a backwash. So in that case, what we're going to do is close our service inlet, close our service outlet, open our backwash outlet, and open our backwash inlet, and now we reverse the flow and we actually expand the bed, and as the bed expands, the particles move apart and allow the dirt and debris then to flow out this way. So, boy, I'm trying to think of applications. I started off my career working in building operations, building maintenance in a very large Olympic class swimming pool that was used for the Pan American Games a couple of times. And so we had one of these here, and it was a gravity filter. Okay. Pressure filters, I think, are a little bit more common. Simply put, it's an enclosed vessel. I mean, what they're not showing on the gravity filter on the left is the overflow. There has to be an overflow on this thing, because if the delta P across the bed gets too great, then the influent water will sort of build up, and it will actually overflow, and we don't want that. Whereas a pressure filter doesn't really have that that sort of stipulation. Now this pressure filter on the right has what's called a graded filter, and so what we're going to have is coarser and finer particles, and what it's going to be is different types of media. So maybe we've got some anthracite, maybe we've got other things, and so these are all different filter media with different diameters. Of media, and also different densities. And so then the way it's going to work is that the stuff that ends up on the bottom is going to be very fine medium, which means small particle size. And the stuff on the top is going to be coarse medium. Which means it's got large particles. And you're probably wondering, well, how on earth can you get large particles on top and small particles on the bottom? It's the densities. So the stuff on the bottom is pretty dense material. So even though the particles are small, it's dense. And here, even though the particles are fairly large, they are less dense. So when you do a backwash, the heaviest stuff goes to the bottom first. So that would be the fine particles, being dense, go to the bottom. And the coarse particles, being less dense, they hang around at the top. They're the last ones to settle. So why do we want this? We want this so that we efficiently use the entire depth of the material. Okay, so you've got a particular bed depth. And what we do not want is called face loading. Face loading would be, let's say I have fine materials all the way through, and so then the dirt particles just go right onto the face, and eventually we end up blinding the filter. So that's face loading. Which leads to blinding. And blinding is high delta P, high delta P across the filter from the inlet to the outlet over very short service run. So short service run. Now, a service means from the time that you put into service until the time you have to take it out to backwash it. So we have service leads to a high delta P, which brings you to backwash, and then we rinse it, and then we're in service again. So that's a service run. And what we'd like to do is maximize the length of the service run. And we cannot maximize the length of the service run if we are continually binding and face loading the filter. What we want is for the particles that come in with the influent to actually penetrate the bed. So that way, instead of face loading, we get all of the dirt throughout the entire depth of the bed, and we call that, in fact, loading. So the opposite of face loading is depth loading. And you can see how we're basically using the filter media more effectively by having those particles actually penetrate into the bed. So depth loading is desirable. Okay, it's more gooder. It's better. And it leads to a long service run. So how do we achieve depth loading? We achieve depth loading with graded filter media. Okay, that was really the long way of going around to address this thing here. the graded filter media. Because if we've got large particles where the water first enters, it becomes easier for it to penetrate into the depth of the bed. So it becomes progressively finer and progressively denser, and we end up filtering throughout the entire depth of the filter instead of only at the surface of it. Make sense? Okay, there are other filter aids that we use, and one of them is diatomaceous earth. And so these here are little microscopic animals called diatoms, planktonic diatoms. So I don't know, maybe they're a kind of plankton, I don't know. And so they were very, I guess, little prehistoric animals, and as part of their metabolic process, they make an exoskeleton. And so these are the little exoskeletons, and they are made of silica. So if you ever find yourself using diatomaceous earth, you got to know that this is not just mud. This stuff here is silica, and it's super, super fine. Obviously, you can see it's microscopic, and this stuff here causes silicosis, which is kind of like asbestosis. So it is dangerous, and you need to wear PPE. You need to wear respiratory equipment when you handle this stuff. And I know this because I handled this for 8 years when I worked at that swimming pool. We used this particular product as a filter aid, and it's very, very commonly used because it has all of these tiny little pores. So it's kind of like little micro filters. And as a filter, this stuff here will actually remove organics. You know, so oily substances and stuff, it actually can filter out stuff like that. So that's one type of filter aid. And so what we will do is take a filter tube, and this filter tube has a sock on it, like a fine nylon sock. And so it's permeable, so water comes in from the outside and then goes through the tube toward the discharge. So it's a nylon sock with a rigid frame inside of it. And what we're going to do is pre-coat this whole thing. So we're going to have a coating on the entire filter made of diatomaceous earth. So what we've just done is made a super, super efficient filter. And then what we will do is we will continue to pump diatomaceous earth into the water that's coming into the filter. And so as dirt particles accumulate, I got a different color for dirt particles. Oh, look at this. This is the perfect slide. Here is, imagine that there's a sock here, that nylon sock. And so we have all of these little diatom skeletons coating that filter. And so that's called our pre-coat. And then what we do is, along with the dirt, we're always adding additional diatoms. And so that way we don't blind the filter. What we do is we continually add pathways for the water to flow. And so what happens then, and this is called body feed, by the way, eventually what happens is you end up with this really thick coating that still permits the flow of water, even though there's lots of dirt in it. Eventually what we'll do is we'll backwash it and we'll slough it all off and recoat it. But as for other filter aids, there are Okay, well, we know about this. Okay, yeah, we've already covered the various coagulants. So coagulants are also considered to be filter aids, and we know what they do. So as for pressure filters, we looked at the iron filters already, and these particular ones are full of anthracite. But the ones you can see here on the left are actually downstream of the lime reactor in the plant where I used to work. So what we would do is, first of all, do some precipitation softening, and any sort of lime that was carried over would get filtered by these pressure filters. So that way the lime would not foul the ion exchange resin that was downstream. So let me just sort of draw a bit here. So here is our aerator, and then we've got an iron filter. And then what we have is a precipitation softener. So we have a lime reactor. And then from the lime reactor, we've got these pressure filters that you see over here. And then the tall one that you see over here is a carbon filter, and it is packed with, I believe, charcoal. So that's this one here, carbon filter. And this one here will remove any organics, because organics also foul ion exchange resin. And then the water goes to the demineralizer bank, which is ion exchange. Okay, so just to give you an idea where the filtration business fits in. So we've got an iron filter downstream of the aerator that gets rid of iron flock, and then we've got a pressure filter downstream of the lime softener that gets rid of lime or any kind of sludge that gets carried over from the lime softener. Now, as for the filter run, so here you can see it's in service. We've got a service inlet, we've got a service outlet. We've also got a backwash inlet, a backwash outlet, we've got a vent, we've got a rinse outlet. So those two are open right now, the service inlet and service outlet, and the water is flowing through the filter medium and out. So we've got a particular delta P. So if I measure the inlet pressure and I measure the outlet pressure, I'm going to record that, and backwash is going to be based upon a delta P. And so you'll have a manual that says, you know, when the delta P across the pressure filter reaches this, or every 24 hours, you need to backwash the filters. So based upon delta P, and also based upon time in service. So that's in service, and so then the next thing what we're going to do is, when it's time to backwash, we're going to close the backwash outlet. We're going to close the service inlet. We're going to open the backwash inlet. And we're going to open the backwash outlet, and we're going to throttle this carefully. So for two reasons. First of all, what we want is a proper amount of bed expansion, because we're going for depth loading, which means that we have to expand the bed so that the filter particles move apart and that the dirt is allowed to leave. So we're going to call that just bed expansion. And the bed expansion is going to depend upon what is our flow, the backwash flow. I don't know why someone's phoning me, but I gotta cancel that. If we don't have adequate backwash flow, we're not going to get adequate bed expansion, and we're not going to discharge all of the material. But if we have too much bed expansion, we're going to start to carry filter material out through the backwash outlet. So we don't want that either. And so backwash, we need to have the correct flow. And we also need to have the correct amount of time. So maybe it'll be backwash at flow X for 10 minutes or something like that. So there you can see the backwash. Then what we're going to do is rinse it. So we'll close the backwash outlet. We'll close the backwash inlet. We open the service inlet. And we'll vent it. Get any air may have been accumulated. Close the vent. And open the rinse outlet. And the reason for this step is we have expanded the bed. And now what we want to do is compact it a little bit. I mean, we don't want to make it hard as a rock, but we want to compact the bed. If the bed is expanded too much, we put into service, then we get channels. And what we don't want when it's in service, we don't want that stuff channeling all the way through. We don't want the impurities getting all the way through the bed. And so the term we use for that is channeling. C-H-A-N-N-E-L-I-N-G. Okay? Channeling is no good. And to help prevent channeling, we need to recompact the bed. And so we're again going to rinse it at a particular flow. Not too much, not too little, just right. And again, that would be in the operating instructions for the plant. We'll vent it, and then we'll close the vent, and then we'll open the service outlet, and we're back in action. So that is a service run from beginning to end. And what we should notice at this point is our delta P would be considerably less. Yeah, so on this particular setup here, you can see we've got an orifice plate here, and the orifice plate has a rotometer, and so basically this is the way that we can determine and fine-tune the flow through the particular filter. Now this is coming from the clear well downstream of the lime reactor, and so this is our inlet, and that's our service outlet. And again, we've got a service inlet for the carbon filter, and you can't see it, but down here is a service outlet for the carbon filter. And so right now you can see that this particular one is in service because the service inlet is open, service outlet is open. And when we want to, oh, and there's the vent. And down here is the drain or the rinse outlet. And so to actually do the backwash, we're going to shut this, and we're going to shut that, and we're going to open the backwash inlet. And so now the water flows this way into the filter, comes up through it this way, and out through the backwash outlet, and then it just discharges down into this pit here that we call a tun dish. Service inlet, service outlet, backwash inlet, backwash outlet, rinse outlet, and vent. Yeah. So here's some stuff. Just want to put this in your back pocket. You don't get tested on this, but this is from the Osmonics Pure Water Handbook. You can find this online. It's free for download as a PDF. It's more designed toward potable water production than it is for powerhouse production, but the same principles apply. And so anyway, so they say that there should be a particular in-service flow rate, and it depends upon the surface area of the bed and the depth of the bed. So you're saying typically a 76 centimeter deep bed that has 1 square of surface area would be 12 cubic meters per hour. So the bed area would be the cross-sectional area of the filter. Because the water's flowing down through it. So just so you know that there are guidelines, right? There are guidelines to the maximum flow or to the design flow for a particular filter. So you might wonder, well, why do they want maximum flow of this to the filter? Well, suffice to say that it's designed that way. As for flow rates, how much backwash depends upon backwash water temperature and the type, size, and density of the media. So ultimately, you know, you're reading up and it says the backwash flow rate should be X when you're doing and you're going, why? Oh, because it's designed that way. So what's the importance of this? We want to prevent channeling. We want to maximize the service run. We want to prevent attrition of the filter media. Now, attrition means loss. And attrition is when we lose material during a backwash. And we don't want to keep losing our filter material. Plus, we want complete release of the captured particle, so we get proper bed expansion during backwash. And the rinse rate, we want bed compaction. Anyway, so interesting stuff do you find when you're on the internet. There you go. Enough of that slide. Let's go back to red. I think it's a little bit more visible. So the next thing, and I think we're going to end it off, we're going to take a look at the cold lime softener. And actually what we should be looking at here, that's the objective. What we're going to look at is the lime soda reactor. And we find that in a few different configurations. We can have a cold one. I'm not sure like a cold one right about now, but it's a little too early in the day. We can have warm, and we can have a hot lime soda reactor. Now, a lime soda reactor might use lime. It might use lime and soda. It really depends what kind of hardness species are in the water that enters into it. So anyway, this is called precipitation softening. And what we're going to do is take soluble dissolved solids Now, what we're looking at here are not colloidal particles. This is not suspended matter. Now we're talking about soluble solids. So what we have is a solution. And recall that when we have groundwater, we are likely to have more dissolved solids because the water's been sitting in the ground. So we've got soluble dissolved solids, And what we're going to do is add chemicals. So we're going to have a chemical reaction. Recall that in the clarifier, we did not have a chemical reaction, but now we're going to have one. And the product from that chemical reaction is going to be insoluble solids. And these particular insoluble solids are going to drop out of suspension. They're going to form a sludge, and we're going to remove that. Now, yes, there is going to be a chemical reaction going on, very, very important. But then the next thing is this insoluble solids are usually very fine particles and fine flocks. And so if you've got fine particles, really they're colloidal. And being colloidal, we want to have flocculating agent. We want to get coagulants. So we are also going to add coagulants, just like we used before, and flocculants. So the coagulants and flocculants are not operating, they're not creating a chemical reaction. Rather, what they're doing is they're taking these fine particles that are precipitates and they're causing them to get together so that they can form a sludge blanket and we can discharge that stuff. So precipitation softening is very important when we have a large bulk. We can call it bulk softening. So let's say we got a lot of water that we need to soften because we've got a lot of makeup water in the system and there's a lot of hardness. Well, yeah, we can run it right through the demineralizer bank, but then we'd have to reach the demineralizer bank every 15 minutes, you know, because it would load up so quickly and so fast. What we need to have is a device that can remove the bulk of it, you know, that's going to remove, say, 90% of the hardness. And so that way the ion exchange resins a little bit further down don't have to work so hard. Now, one of the things that is absent from your fourth class is the term temporary hardness and permanent hardness. Were those terms when you guys studied this stuff last year?
I don't recall hearing those terms.
Okay.
I think they might have been
So,
by the lab instructor once or twice, but not in the books.
okay. So let's just take a look at a couple of types of hardness. Now, we know that magnesium and calcium are both in the same family. They're both in the same group. They are alkaline earth metals. And so magnesium and calcium really form the same type of compound. So we can have calcium bicarbonate or we can have magnesium bicarbonate. We can have calcium sulfate and we can have magnesium sulfate. Now, let's say I've got that stuff in solution. Those are both soluble salts, and they're in solution and they go into a heater. And let's say that the water leaves at 100 degrees Celsius. What we find then is certain species, the bicarbonates, are going to deposit as scale. Whereas the sulfates and the chlorides persist. So I'm just going to put sulfates, chlorides, that's 2 plus, that's just, pardon me, 2 minus, and the chloride is just minus. So these species persist, but the bicarbonates form scale. Now these ones aren't going to persist for long because when they get to a higher temperature, they're going to drop out as well. And they're going to form a very hard scale inside of a boiler. So here's the thing, is in the early days when experimentation was being done, they found that the bicarbonates did not persist beyond 100 degrees Celsius. So they're soluble below 100 degrees Celsius. Once you get to close to 100 degrees Celsius, they actually drop out of solution. So when they're doing the experiment, they found that certain species continue through. So they decided to call the ones that dropped out below 100 degrees as being temporary, meaning they could be removed just by heating water. And the ones that persisted and went into the boiler and caused more trouble there were called the permanent hardness species. So the sulfates and the chlorides. And there is a mistake here that calcium carbonate is not a dissolved solid, it's an insoluble precipitate. So the big question is, how do we get rid of temporary and hardness? Well, the temporary hardness, we deal with something called lime, and lime is calcium hydroxide. And the permanent hardnesses we deal with by adding something called soda ash, where we get the term soda from, and soda ash is sodium carbonate, as well as a coagulant. And what it's going to produce are insoluble reaction products. So it's going to produce calcium carbonate, which is going to precipitate, and magnesium hydroxide, which also precipitates. So let's take a look at the first set of reactions involving calcium hydroxide. Now this is going to be for temporary hardness. So we have calcium bicarbonate as one form of temporary hardness. Calcium bicarbonate plus calcium hydroxide yields calcium carbonate, which is a precipitate, and water. Pretty cool. So this stuff here is junk that ends up as part of the sludge. We're going to blow that off. And then, of course, the water, that's a good thing, right? Now, if it's magnesium bicarbonate, now usually both of these species are present. Sometimes you'll have more magnesium, sometimes you'll have less. But regardless, you got magnesium bicarbonate coming in, plus the calcium hydroxide gives you magnesium hydroxide, which is a flock. And that's very important. The formation of magnesium hydroxide, you're going to see, is going to be very, very important for us. It will actually attract other particles, and the formation of magnesium hydroxide will also remove silica. Because what we find is that silica will adsorb onto the surface of the magnesium hydroxide flock as it forms. Then it makes calcium carbonate, which precipitates, which we blow off, which is our sludge, and water. So lime does a really good job of removing temporary hardness. But it does nothing for permanent hardness. So let's just take a look at what's going on with the permanent hardness. Now this is magnesium sulfate as one form of permanent hardness. This stuff is going to form hard scale in your boiler. It doesn't drop out at low temperature, but it drops out at the higher temperatures in the boiler. So here's lime plus magnesium sulfate makes magnesium hydroxide, which is a flock, and it makes calcium sulfate. Okay, this is still hardness. And we'll get back to this one on the next slide. Magnesium chloride as being the chloride hardness species, plus calcium hydroxide, the lime, is going to again give me some magnesium hydroxide flock, plus calcium chloride, which again is hardness. So what we have to do is deal with the calcium sulfate and calcium chloride, and we do that with soda ash. So the calcium sulfate and the calcium chloride that we saw on the other screen, there's the sulfate, there's the chloride, plus sodium carbonate gives me either sodium sulfate or sodium chloride and calcium carbonate, which is a precipitate. So the combination of lime plus soda gives you those 6 reactions that basically remove all of the hardness, and recall that hardness is always magnesium and calcium salts of bicarbonate, sulfate, and chloride salts. Those are basically what we're trying to get rid of. Which brings us to our to the end of the day. There's a summary page, and this is all stuff that is covered in your PanGlobal as well. So you should really know these reactions.